Welcome to The Explainer. Today, we're taking a look under the hood of the electric vehicle revolution. When we think of modern EVs, our minds almost always go straight to those massive battery capacities, the instant torque, or maybe those giant futuristic dashboard screens. But there's actually a secret to an electric vehicle's performance and safety. It's this invisible guardian that quietly dictates how far you can drive, how fast you can charge, and, quite frankly, whether your car actually survives the trip. But before we reveal exactly what that guardian is, let me ask you a question. What do you think is the single biggest threat to an electric vehicle's performance? It's not running out of charge on a long road trip, and it's certainly not some random software glitch in the dash. No, it's something way more fundamental and incredibly physically demanding. The answer is heat, specifically the immense, intense amount of heat generated by the battery itself. See, in electric cars, just the simple act of discharging the battery generates heat. And the faster you discharge it, like when you're mashing the pedal to merge onto a busy highway, the more heat it kicks out. This isn't just some minor inconvenience we can brush off. It's a massive engineering challenge that can literally make or break the entire vehicle. Okay, let's dive into this. To truly understand why heat is the ultimate enemy here, we have to look at the underlying chemistry. So, batteries operate on a principle called a voltage differential. But when extreme heat enters the picture, it physically excites the internal electrons. Imagine those electrons acting like this highly excited, totally chaotic crowd inside the battery cell. This chaotic excitation drastically drops the difference in voltage between the two sides of the battery, which effectively ruins its ability to deliver power or even hold a charge. And because these batteries are manufactured to only work within very specific temperature extremes, they require a strict Goldilocks zone just to survive. That range is incredibly narrow. We're talking about 20 to 40 degrees Celsius. If the battery pack falls out of this working range and there's no cooling system to rein it back in, the battery will literally just stop working. But wait, the engineering challenge gets even more precise than that. It's not just about the overall average temperature of the car. The internal temperature difference within the entire battery pack can never exceed this tiny, tiny margin of just 5 degrees Celsius. If you get a larger internal temperature difference between different parts of the pack, you end up with uneven charge and discharge rates for individual cells, and the whole battery pack's performance will rapidly deteriorate. So what happens if this invisible guardian fails to maintain those completely uniform temperatures? Well, the consequences are severe. We aren't just talking about your battery losing its charge a little faster over the years, which is known as capacity degradation. We're talking about severe thermal stability issues. If a battery overheats or even just has a non-uniform temperature distribution, it can trigger thermal runaway, which leads to a catastrophic fire and explosion. These are absolute life-threatening safety issues. Section 1, 4 cooling contenders. So how on earth do we solve this high-stakes heat problem? Over the years, engineers have basically tested 4 major cooling contenders: phase change material, fins, air, and liquid cooling. And when we walk through the data, the fatal flaws emerge pretty quickly. Take air cooling, for instance. Sure, it's simple, but it needs 2 to 3 times more energy just to maintain the same average temperature. Fins? Well, they transfer heat great, but they add about 40% extra weight to the cell. No thanks. And phase change materials can absorb heat well by changing from a solid to a liquid, but they can't transfer it away effectively. Plus, their physical volume changes drastically, which leaves us with a clear, undisputed winner. The absolute champion is liquid cooling. Liquid coolants offer the highest heat conductivity and heat capacity, which basically means they have this incredible ability to store heat right in their chemical bonds. Liquid cooling hits all these strict thermal requirements without sucking up too much parasitic power from the battery, and it fits super compactly right into the pack. This is exactly why major manufacturers like Tesla, Jaguar, and BMW all absolutely insist on liquid cooling systems. It's simply the safest, most effective method out there. Now, what's really interesting about this slide is what actually makes up that champion liquid coolant. You might think it's some highly exotic, super top secret proprietary fluid, but actually, a massive 99% of it is just a standard commodity like glycol and water. But it's that tiny 1% additive package that separates basic, everyday fluid from world-class engine protection. That 1% is the secret ingredient that literally saves the car from destroying itself. So why is that tiny 1% absolutely critical? In a word, corrosion. When you're circulating a liquid coolant throughout metal piping, metal naturally wants to react by losing electrons to reach a more stable state. Positively charged impurities in the coolant fluid interact with the metal pipes and strip away the surface layer. Without that 1% additive package that's specifically blended to protect against rust and scale, the internal metal pipes of the EV cooling system would literally be devoured from the inside out. Section 2, direct versus indirect cooling. Now, liquid cooling isn't just taking a garden hose and pumping water onto a battery pack. There are actually two completely distinct approaches here. On one side, we have indirect cooling. This is a lot like the familiar plumbing you'd find in a traditional internal combustion engine. It circulates the liquid coolant through a complex series of metal pipes to pull the heat away from the battery pack. On the other side is direct cooling, which, I gotta admit, sounds a bit like science fiction. In a direct setup, the actual battery cells are fully submerged and in direct physical contact with the liquid coolant itself. Direct cooling brings some absolutely incredible thermal benefits, but it also introduces extreme danger. Because the battery is directly exposed to the liquid, it requires entirely new types of coolants. These fluids absolutely must have low to almost zero electrical conductivity, often relying on deionized water or non-salt-based mediums. Think about the stakes here for a second. You've got electrons flowing all throughout that battery. If you submerge them in the highly conductive coolants we use in traditional engines, those electrons would immediately flow out into the fluid, causing a massive catastrophic failure, or worse, a fiery explosion. Section 3. The future of coolants. Now, these direct cooling schemes are still heavily in the R&D stage, so you won't see cars on the market using them quite yet. But as we look toward the horizon, the rapid evolution of electric vehicles makes this technology vital. Our source material notes, as the electric vehicle grows, there is and will continue to be high demand for longer battery life and higher power output. And this brilliantly illustrates the core challenge going forward. Higher power output simply means charging and discharging at much higher rates. That translates to way more stress and, crucially, a lot more heat. So the continued research and development of these specialized, low-conductivity coolants is definitely the crucial next frontier for EV safety and performance. Which leaves us with a final, rather provocative thought. As EVs continue to charge faster and drive further, completely pushing the absolute limits of physics and battery chemistry, what new coolant will be engineered next to keep them from burning up? The answer to that question is going to define the entire next generation of electric vehicles. Thank you so much for joining me on this explainer. Hopefully, you now have a much better understanding of the invisible guardian protecting your battery, and you'll be keeping your eyes peeled for those quiet chemical innovations keeping us all safe on the road.